Feel free to ask me any questions if you have any. We got a couple minutes for class. Oh, nope, we're actually supposed to start right now. Boop. We only have like four people in here though, so we can't really get anything started, but you're still free to ask me questions. I'm going to give it a couple more minutes before we start just because I want to give enough time for some other people to get in here.
The lab instructor was wondering when the first test was.
Yeah, she sent me a text message. I just got it about 30 minutes ago. So she's shooting for 7:30 as the first practice test. Let me double check to make sure that's what I remembered. Ours is the first face-to-face test. Oh yeah, I said 7:30. I meant 5:30. So on the 30th of this month, that's what she's shooting for the first test to be. So that's what I'm going to try to make it for. That I'm in the process of integrating it into your syllabus, so we'll have that. But I did want to wait on her because I wasn't really sure how she would want to do it. So
Will
anything?
that be on chapter 17 and 18?
Yeah, it should be 17 and 18. Given that it's on the 30th, I know that can't be right. No, that's too early. The 30th is literally 2 days from now. That's not cool. No. Uh, I'm
I
not
think she
sure.
said
Go ahead.
I think she said that she would cater it to what you were thinking to
Yeah.
do it.
I got that from her today, and I just told her thank you. So I'll communicate with her tonight and try to figure something out. But definitely, there's no way I'm going to give you a test on the 30th. Now, I might have a online test that's going to be open in this today or tomorrow, and you'll have until Monday to get it done. That's just going to be an online test, and that will cover chapter 17 and 18. But I'm not going to make your first face-to-face test that early. I don't think I can. That being said, normally what we try to do is get one face-to-face test in before the drop date, but I think the drop date's a little later than that. I could be wrong, but that might be why she particularly chose that, is just to be consistent with it. But I'm not really sure. I'm really kind of bummed that I only have four people in the class, though. That worries me. It makes me think people got scared and might be considering dropping or something. But anyways, I'm going to use this time, this brief second here today is the 28th. And I'm checking the roll just by the names that are listed up here. So I got that one. I got that one. And I got that one. I got that one. So I've got the four of you that are here. I've got your roll taken. If other people get here, I'll be able to get that later. But the main thing is I just want to get that knocked out. So does anybody have any questions on chapter 17? Yes. So Ava just asked, will I change the due dates for practice test and chapter 18 homework? I literally did that 2 seconds before class started. So let me let you know what I actually have in terms of due dates for tests and whatnot. So if I look right here, I've changed the chapter 17, both the conceptual and the chapter 17 problems are now due on 6/3, so that's June 3rd, which I believe is Monday at 11:59 p.m. That's 17 homework and 17 conceptual. 18 conceptuals also due on 6/3, but 18 homework will be due on, it's supposed to be 8/5, but I accidentally put it to 5/5, so that's not good. So I'm gonna fix that real quick. So let me fix this. So I have already pushed those due dates back, so hopefully that's good. Darn it. So 18 homework will now be due on June 5th at 11:59 p.m. So 6/5 at 11:59 p.m. is 18 homework. 6-3 at 11:59 p.m. is 18 conceptual, 17 homework, and 17 conceptual. So all that's set up. I did get another student just rolled in. So I'm going to put their name on the roll sheet. And I have that one. Good. All right. As I told you guys, y'all, these names might pop up on my YouTube channel. So if you don't want any of that showing up, make sure you change your username to, I think I spelled it out in the syllabus and everything. So basically use like your first initial of first name and your first initial of your last name, and then follow it by your your last three student ID numbers. And since you're in the class, you don't have to put the class, but if someone was here from another class, then they would. All right, now I got another person here too. Gotcha. Okay, so now it's looking like we're only 2 shy of what we had last time. So hopefully those 2 students will show up, and that should be fine. So we were asking about having questions. What I'll tell you, since 2 people came in since then, is yes, Miss Raskovic and I are sort of working through the details. She did list 5:30 as the first face-to-face test day, and that's just 2 days from now, so I can't do that. So I'm going to at least push it back, but there will be a a online test that I'll make it available tonight if it's not already. The practice test will be available as well. Actually, the practice test has been available for some time, but the actual test will be available sometime tonight. And you'll have until, since you meet on Tuesdays and Thursdays, I'll let you have until Monday night, which again is June 3rd at 11:59 p.m. So, I got that too. Okay. So Monday night, 11:59 p.m., your first online test will be due. Make sure you don't miss that. Missing a test generally gets you a 0. I do drop one of the lowest, but you wouldn't want to waste a dropping grade on just missing one. So make sure you get it done. The best thing I can recommend you do is every day of the week, I would just go on to Canvas and check for what's due. Especially check like the day before class. So for instance, your classes meet on Tuesdays and Thursdays. So I definitely check, for instance, Monday and Wednesday to look for something to do, because they're normally due 11:59 the night before. So I definitely do that. Any questions? All right, well, let's
The
get
online test, open notes.
Yes, with the online test there, you can do open notes, open book, open Google searches. I used to. I'm probably leaning away from that. I tried to keep students honest by limiting the amount of time per question that they had on in general. Even though it wasn't really per question. It was like I averaged a minute and 10 seconds for each question over 20 some questions or something. And that was an attempt to say if you had to look up more than one of them, I would hope it would cause you to go over the time required, and therefore you'd end up losing points, because I want you to maybe miss one just because you didn't understand that material, or you didn't get to that material, or it was just hard or something like that. That's very normal to miss that sort of thing, but if that happens, I want you to have the option to look it up and try to figure out, what you did wrong or what you don't remember or something like that. So you can do that. But if you have more than one out of that, 20 questions or whatever, I think that's the point where you haven't learned so much as you're just maybe memorizing stuff. So that was my whole impetus for shortening it. But I discovered there are some students that work so slow that forced them to do nothing but Google the answers. So I tried to open that back up, and I'm going to leave that back on you guys to be responsible for knowing if you're using stuff too much or not. So that's a hard thing for me to tell you to do, because it's real easy to convince yourself that you're learning when you're not learning. So be very careful about that. If you find that you look up more than one problem on the practice test, that's a good indicator that you're not ready. If you find that you look up more than one question on the actual online test, that means you're definitely not ready. You can have time to get it done, and that's fine, but you want to do better the next time. Okay. All right, so hopefully this works out. So we are starting now chapter 18, and it's called The Kinetic Theory of Gases. We'll tell you that the sections, according to Giancolli's 5th edition, the sections are 18.1, the ideal gas law, and the molecular interpretation of temperature. That's what we're going to start off with a neat derivation. 18.2, the distribution of molecular speeds. I'm going to actually give you an equation worked out with even more robust statistics that gives you the distribution of the speed. I'm going to give you in section 18.3 real gases and change of phase, tell you sort of what's going on. 18.4 vapor pressure and humidity. 18.5 is temperature decrease of boiling water with altitude. 18.6 is van der Waals equation. Other than just the simplest of checker questions where they give you the extra little variables and then you just sort of solve it like it's an ideal gas law, then that's pretty much what you can be expected to do on van der Waals or nothing on the test. Mean free path, I want you to read that and do homeworks on it, but I'm not going to test you on that, and I'm not going to test you on diffusion. Okay, so I'm not testing you on 18.7. I'm not testing you on 18.8, mean free path and diffusion. Van der Waals, like I said, I reserve the right to ask you a very straightforward, simple van der Waals equation question, but that's about it. So let's get started. Again, you should, when you're reading the book, when it has like a chapter opening question, I do want you to take the time to ask that. And if you feel like you're just guessing, that's okay. Guess, but use as much logic and reason as you can so that you can correct yourself later. And then don't feel bad about having made a false hypothesis. That's as I've tried to beat in my students' head, a false hypothesis is way more useful than a true hypothesis in general over the history of mankind. So let's start off with the idea of an ideal gas law and the molecular interpretation. To do that, there's a couple different versions of the ideal gas law. I've already given you let me write it down here. So I'm going to go ahead and share my screen with you guys. Okay, I'm trying to share it with you guys. Oh, there, now I'm getting it. Okay, so I had an ideal gas law. And actually, I want to look up my constants just to make sure we're all on the same page with that. So I think I gave it to you last time too. So what we have for the ideal gas law, one version is PV, and I normally write the P lowercase and the V uppercase, but your book seems to do everything in caps, and that's okay too. I would just tell you that I have a reason for doing that, but don't worry about it too much. And when you actually take engineering thermodynamics, you'll learn probably some of the reasons why we do lowercase and uppercase and that sort of thing. But in this case, R is equal to 8.314, and that's joules per mole Kelvin. So if you have the pressure in cubic meters, if you have the temperature in Kelvin, which is what it has to be, and you have the pressure in newtons per square meter, then this is the R value to use. However, if you have if you want to use the R value of 0.0821, now in that case, it's liters, atmospheres, over mole times Kelvin. So again, like I told you, the temperature always has to be in Kelvin for any ideal gas law equation. But in this case, if you use 0.0821 for the ideal gas constant, then the pressure can be in atmospheres and the volume will be in liters. So that's another example. And then finally, there's a third version, 1.99. And in that case, it's 1.99 calories per mole Kelvin. And actually that calorie, the C turned into a sort of an O looking thing. So I'm going to correct that a little bit. And that should be a lowercase c, by the way. So let me undo that. Okay, so in that case, you can see it's not a real easy conversion. Let me let me tell you that way. But the general problem is when you use calories, unlike a joule, which is another unit of energy, a joule is a Newton times a meter, and a volume unit is a meter square, or excuse me, a meter cubed. So you can see how the joule plays in with the 8.314, but in the case of the calories, it doesn't play out that well. So I'm not, well, you'll just see some examples from the homework where you can use the 1.99, but I can't really think of one off the top of my head right now. I'll see if I can find you one and make sure we work an example with it. Now, the other version of the ideal gas law, or another version, was you could say if n/m equals a constant. In other words, you're dealing with a closed container, a sealed container of gas. If that's the case, then you can see that P and V over R, or excuse me, P and V over T is just N times R. R is a constant, at least in the physics world where we do the ideal gas law. And N, since it's a closed container that doesn't allow atoms or mass to go in and out, then N is also a constant. So another version that we use for the ideal gas law is P1 V1 over T1 is equal to P2 V2 over T2. Now, if other things are true, like if V is also constant, then you'd have P1 over T1 is equal to P2 over T2. Or, oh, excuse me, that's right. Or if P is also a constant, then you can have V1 over T1 equals V2 over T2. Okay, so that works as well. Or if T is also a constant, then you have P1 V1 equals P2 V2. So all of those are different ways in which you can implement the ideal gas law. And I think you can see why those three are equivalent, even though this one kind of got jacked up. Just because we're taking the part of the ideal gas law that is a constant, and we're sitting that on one side, and all the other variables, P, V, and T, for instance, are on the left-hand side. So that allows us this first version, P1 V1 over T1 equals P2 V2 over T2. But if we add to the fact that N and M or N or M is a constant, and say that V is also a constant, then you can have the V's cancel out on each side, and you get P1 over T1 equals P2 over V over T2. Or if you have P is also a constant, and you have V1 over T1 equals V2 over T2. Or if you have T is also a constant, then you have P1 V1 equals P2 V2. So those are a bunch of different ways you can use the ideal gas law. And there's actually, I'm just looking real quick to see if they had one where they used that other version of the gas constant being 1.99, but I don't see one jumping out at me. I don't remember using that except for maybe once or twice in chemistry. I don't think I've ever used it in physics to my knowledge, but in principle you could, and I'm just not seeing one that jumps out at me right now. Now, the other version of the ideal gas law that I wanted to point out to you is you can, in principle, say PV equals nRT. So PV equals N times R times T. But what N is, strictly speaking, N is the total number of atoms big N is the total number of atoms. Little n is the number of moles. So you could say that little n is the total number of atoms divided by Avogadro's number. And I'll say atoms, but hopefully y'all know that means atoms are molecules. So you can replace the little n with n over Avogadro's number, and then you still have the R and the T. And I'll say this right here is Avogadro's. I'm trying to remember. Yes. I thought it was AVO, but for some reason I was going with AVA now. Avogadro's number is what that is. So if you do that, then you can say, well, this is equal to N times R over NA times T. That A is a subscript, by the way. So let me make sure you guys know that. I'm going to do that by erasing this right here. And I'm going to say this is the big N and this is the A subscript. Now, what we're going to do is define another constant, and we're going to say this is big N times the Boltzmann constant times T. So that's the result I was really going for. Let me box off all of them. This is one. This is one. This is one. And this is one. And that's got to be true. In this case, that's got to be true. In this case, that's got to be true. And in this case, that's got to be true. But now what we have is also PV equals NKB times T. And this is, in fact, another version of the ideal gas law. And KB, which is defined to be R over Avogadro's number, is 1.3807 times 10 to the negative 23rd joules per Kelvin. So that's another version of the ideal gas law that we can use. For instance, if you don't know the number of moles, or you don't even know necessarily the mass, then you might need to use the total number of atoms or molecules, and that can do that. Okay. But that's another way. And this is going to come in handy with the derivation we're getting ready to do. So that's why I wanted to make sure I clarified that for you. Does anybody have, or clarified, does anybody have a question regarding any of that stuff? Okay, so let me tell you what an ideal gas is. And I'm more or less reading exactly what your author said, because it's not very many authors take the time to write all this out. So I was really happy with Gene Coley doing it. But the opening paragraph, this is section 18, subsection 18.1. So I'm going to write this here. So we make the following assumptions about the molecules in a gas. These assumptions reflect a simple view of a gas, but nonetheless, the results they predict correspond well to the essential features of real gases that are at low pressure and far from the liquefaction point. So ideal gases, first thing I want to say, ideal gas law. Actually, I don't want to do that. That was an ugly L. Ideal gas law works best with, as it said there, these assumptions reflect a simple view of a gas, but nonetheless, the results they predict correspond well to the essential features of real gases that are at low temperature. Excuse me, I said temperature, but I think it was supposed to say pressure. Yes, it was. Works best for gases at low pressure and far from liquefaction. So that's one thing. Now, what does it actually mean to be an ideal gas? That's what I'm going on here. So it said real gases are mimicked by ideal gases when the pressure is low and they're far from the liquefaction point. Under these conditions, real gases follow the ideal gas law quite closely, and indeed, the gas we now describe is referred to as an ideal gas. The assumptions representing the basic postulates of kinetic theory for an ideal gas are: one, there are a large number of molecules, capital N, each of mass m, moving in random directions with a variety of speeds. This assumption agrees with our observation that a gas fills its container and, in the case of air on Earth, is kept from escaping only by the force of gravity. So number one is N is very large. N is the number of molecules, and we also assume that they're made of identical molecules, each of which has a mass m. So I'm going to write this as rule 1, N molecules and N is way, 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 way greater than 1. And each molecule has a mass m. Okay, so N is going to be super huge. 10 to the 22nd, for instance, is a common one. Number 2, the molecules are on average far apart from one another. That is, their average separation is much greater than the diameter of each molecule. So large separation of molecules. So what I'll say is L is much greater than D, where D is the diameter of the molecule, and L is the spacing. Okay, well, that really went badly. So if you say, what is the average distance between the atoms, that quantity we would call L, and I'm saying that I'm going to call that the spacing. So that's number 2. Number 3 says the molecules are assumed to obey the laws of classical mechanics and are assumed to interact with one another only when they collide. Although molecules exert weak attractive forces on each other between collisions, the potential energy associated with these forces is small compared to the kinetic energy. Okay, so molecules are assumed to obey classical physics, and that means Newton's laws, no quantum mechanics. So classical physics is obeyed, and potential energy between atoms, potential energy between is much, much, much less than the kinetic energy of the molecules. So what we mean by that is we basically assume that the energy is so high that the kinetic energy is so high, molecules will blow by each other really, really fast. And the effect that one atom has by attracting the other is negligible. That's what we're saying with rule number 3. Number 4, collisions with another molecule or the wall of the vessel are assumed to be perfectly elastic, like the collisions of perfectly elastic billiard balls. We assume that collisions are of very short duration compared to the time between collisions. Then we could ignore potential energy, associated with the collisions comparison to the kinetic energy between collisions. So this is sort of a build on for part 3, where they're saying the attractive forces between them is not going to be a big deal, but more specifically, all collisions are elastic. All molecular collisions. And that should be somewhat obvious just from the fact that at the microscopic level, where could the energy be going to make it no longer elastic? Because non-elastic collisions are usually due to, for instance, one molecule hits another molecule and causes it to be distorted a little bit, or causing it to vibrate and make sounds. We can't make sounds at that microscopic level because the only thing to carry the actual sound is molecules and atoms, and we're at the size of molecule and atoms. So that's somewhat self-explanatory, hopefully. If not, just think about it a little bit more. But now that we have that, we can now try to make an idea of what the actual pressure of a gas is. So what we're imagining with regards to pressure of a gas is that the individual molecules in the collection of gas is going to basically have the molecules running into, say, the container holding the gas. And when it hits it, it'll bounce off. And if you take the average of however many particles or however many molecules are going to hit that wall per second, you'll get basically the change in, or you'll recognize that that is actually due or creates the pressure that you feel. So when we say a gas has 1 atmosphere of pressure, which we know is about 14.7 psi, which we know is about 1.01 times 10 to the 5th Pascal, we're saying that is due specifically to a large number of molecules hitting one side of the wall and bouncing off at any instant in time, and that maintains that constant pressure because on average it's about the same. So we're going to use that idea to reach a conclusion about how big that pressure is. So what I'm going to do is I'm going to take a XYZ coordinate system. I'm going to call this my x-axis. I'm going to call that my y-axis. I'm going to call that my z-axis. Actually, no, I'm going to change up on that a little bit. So let's try. I really would like the x to point from left to right. So I'm going to say, whoa. So I'm going to say the x-axis is actually this one. And then I'll say the y-axis is actually this one, and then the z-axis will be that one. Notice I have made a right-handed coordinate system, which is, essential. So I'm going to say that, this box or this container that the gas is in is basically this one right here. So that's actually the box. Now, what I'm going to imagine is that there's little atoms, let's say, or little molecules, and we're going to treat everything like it's a molecule. But this is a little molecule. It has a mass m. It has a average velocity v. And in fact, that velocity will have a component that is a y component of velocity. There's a x component of velocity. There's a z component of velocity. So we could say that it goes something like this, where this would be vx, this would be v. Oh, that would be v. Yeah, this would be vx. This one right No, that would be Vy. That's what it is. Sorry about that. Let's make it a little bigger. And actually, let's not try to draw it in there. I'll make a zoom in of it and I'll draw it there. So let me fix this again. So this is our velocity in general. And this is our molecule. Now, what I'm saying about this is this is a picture of the molecule. This is the picture of the velocity. And what I'm saying is this velocity has a component that's parallel to the x-axis. It has a component that's parallel to the y-axis. And then it has a component that's parallel to the z-axis. And I might not have said that in the right order. That's okay. I'm getting ready to explain it by writing the symbols here. So you can see that this one, this vertical line, is actually parallel to the y. So I'm going to say this one is v sub y. I'm going to say this one is v sub x. And this one is v sub z. And the total velocity is just v. So now y'all can see how it's worked out in 3 dimensions. And in fact, v is equal to the square root of vx squared plus vy squared plus vz squared. Okay. Now further, I'm going to say that this wall or this box has a length L going from left to right, because that's kind of important the way we're wanting to do it. So I'm going to call that quantity L. I'm not actually specifying the other ones, but I will say, for instance, that this wall right here, let's do a different color than this. Let's say I'm going to use this color green. So the area of this end of the box, which is the same as the area of the opposite end of the box, is in fact an area A. So we're making the argument, we're making the argument that this face has the same area as the face I just finished drawing. So what's going to happen here is this molecule is going to run and bounce off of that wall right there. And then it's going to bounce back off like this with some velocity v final. And in fact, since it's conservation, since it's a elastic collision, the only way this is possible is if the velocity before the collision is exactly the same as the velocity after the collision. So now that I have that, I can actually start doing some calculations. What I want to do is figure out what the actual change in momentum is, because we know P is equal to force divided by area, and we know force is equal to delta P over delta T, at least on average. Okay. So if we can calculate delta P, that'll be helpful. So just imagining that one collision, what we see is delta P is equal to M times delta V. Now, all that really concerns us here is trying to calculate the pressure on that left side of the box or that right side of the box. Specifically, I'm working on the left side of the box. Okay. So what I know is this is going to be M times parentheses, the final velocity. In this case, we're going to say all of this is about the X momentum. So I'm going to put a little subscript X there and a little subscript X there. And what I'm going to say here is this is going to be V sub X minus negative V sub X. Okay, because as I showed you, the V sub X has a negative component in that larger picture right here. So note v sub x is less than 0 because it points in the negative x direction. Whereas v sub x in this case is greater than 0. Does that make sense to everyone? So the change in momentum, delta p, actually, let's go back to purple. The change in momentum, delta p sub x, is going to equal m times 2 v sub x, like that. Okay? So that helps us a lot. That gives us a opening idea of what the change in momentum would be due to a single molecule of mass m moving with an x component of velocity v sub x in the negative x direction, then bouncing off the left box wall and moving off in the positive x direction with a momentum m vx, the exact same magnitude vx, but now the vx is in the positive direction. Now, what we'd like to know is over how much time does this take place? Because ultimately what we want to know is delta P over delta T to get the F. Well, if you notice, no matter what's going on in the Y direction and Z direction, that's not going to interrupt what's going on the left face, because the molecule is going to go up and bounce off the left face. If it had no X and Y components, then it's going to immediately bang off of the left face and head horizontally back to the right face, bounce off that, and head horizontally back to the left face again. Since it actually has, for instance, a component of velocity other than x, let's say thinking about the z component, well, it could actually go up and pull towards the direction outside of the page. So it's trying to come out towards us and bounce off the wall. And then that wall, since it's not absorbing any energy because it's an elastic collision, then the z component of velocity is not going to change at all. So it'll just sort of bounce off the wall and keep going with the same v sub z. Similarly, if it had a y component, then it's going to go in the upward direction and to the left. So it's going to bounce off the wall. Again, no energy is going to be stolen from the molecule as it hits the wall. So the v sub y is not going to change. So it's going to take off with basically an x component, a y component, and a z component. But the z component is just going to tell us something about how often it'll hit the front face or the back face. And the y component is just going to tell us something about how often it's going to hit the top face and the bottom face. Whereas the x component is going to tell us how often it'll hit the left face and the right face. So what we're going to say is if you take the distance L and you multiply that by 2, then that's the total distance left and right that the molecule has to move after hitting the left face before it hits the right face, and then, or excuse me, before it hits the left face again. So it'll leave the left face, bounce off the right face, and then return. Now the distance it traveled, at least parallel to the x-axis, will be 2L. So since velocity equals distance divided by time, we know that delta t would be equal to distance divided by v. So what I'm going to say now is delta t is 2L over v sub x. Okay? Because again, yes, it's going to be moving towards the front face, moving towards the back face, moving towards the top face, moving towards the bottom face, but none of that's going to cause it to slow down or speed up in the x direction. So all that's going to go is this thing's going to consistently go bang, 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 or at least a shadow of it will along the x-axis. Does that make sense? All right, so if we want to calculate the force, feel free to type in. Let me actually put up the chat window in case anybody's already chatting something. So I don't see any chats. I do see where Ava asked a question about being due Monday night. Yeah, we addressed that. Cool. So what I want to do now is realize that F, the force that the wall has to supply is, at least that left wall is going to supply, is delta P over delta T. And if the time interval is small enough, that really becomes a differential P over dt, which is exactly F as opposed to approximately F. So what we've already calculated is that delta P specifically is going to give us 2m v sub x. All of that's divided by 2L over v sub x. And what we get is that the 2 is going to cancel out with the 2, and the v sub x is going to square. So ultimately what we get is m v sub x squared over L. Okay, so that's the force that the wall has to apply in order for this to, for that one molecule to be bounced back with the exact same speed, conserving kinetic energy. Does that make sense to everyone? So that is force the left face must supply for one molecule to have an elastic collision. With the left face. Okay, but for N molecules, then what's going to happen is F is going to be M over L, because that's not going to change. M, the mass of the atom or the molecule, not going to change. L, the distance perpendicular to the left face and right face, is not going to change. But what we're going to have is Vx for the first molecule squared plus Vx for the second molecule squared plus dot 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 plus on up to Vx for the nth molecule squared. So that's going to give us a ton of individual terms. In other words, 10 to the 22 terms is not unreasonable. Well, we know that the average of the square of the velocity would equal Vx1 squared plus Vx2 squared plus dot 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 Vxn squared, and then all of that you divide by n. Does everybody see that that's just your normal averaging process? So if we wanted the average of the square velocity, we would just take each velocity, square it, and then add them all up. There's n x components because there's n molecules. So we'd have to take all n of them, square each one of them, add them up, and then divide it by n. Since that's the case, we can now see, for instance, that this quantity right here is the same as this quantity right there. So we can now do this a little differently and say that F, so I'll put these little marks that mean therefore, F total is equal to, and I should say total there too, because that's a little different than the L, the F that we had before. This is for one molecule. So for N molecules, what we're going to have is M over L. And then in place of that, Vx1 squared plus Vx2 squared plus Vx3 squared plus dot, 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 we're now going to have N, we're now going to have capital N times Vx squared bar. Does that make sense to everyone? Now, this is all in terms of just the x component of velocity, which is going to be random. There's going to be a random distribution or some seemingly random distribution of velocities, period. And they're all going to have x components, y components, and z components. So each of those components are going to be random. So what we'd ideally like to do is take it in terms of the average random velocity, not the average random velocity component. So what we do know is that v squared is equal to vx squared. Oops, I wrote that backwards. Is equal to vx squared plus vy squared plus vz squared. Okay. And in fact, if you wanted to take the average, you could say, well, the average of v squared is equal to the average of vx squared plus the average of vy squared plus the average of vz squared. Now, the other part of it is basically that there's something called the equipartition theorem that basically says that Vx squared on average is equal to Vy squared on average, and that's equal to Vz squared on average, because there's no reason to assume the x direction or the y direction or the z direction is a preferred direction or has something that's causing it to be slightly bigger. Therefore, statistics of very large numbers are very specific about exactly, if you have three different places for the energy to go, exactly 1/3 will go in each of them. That's what this is saying, hey, the average x squared should be equal to the average y squared should be equal to the average z squared. So if I combine these two together, what I get is v squared average would equal 3 Vx squared on average, because Vx squared is equal to Vx squared. Vy squared is also equal to Vx squared, and Vz squared is also equal to Vx squared. So I can just say Vx squared plus Vx squared plus Vx squared is equal to V squared. And now I can see that by plugging this back in, I get V squared on average is equal to 3Vx squared on average. And because of that, I can now change the F total to M over L times 1/3. So I'm going to do 1/3. Now I'm going to write that N on top because it was already there. I'm going to write my M on top because it was already there. Now I'm replacing my Vx squared with just plain velocity squared on average. And then all of that is going to be divided by just plain L. Oops, did I get everything right? Let's see. V squared L M over L. Yeah, that all works fine. N mv squared L. Yeah, all that's fine. So pressure is equal to force divided by area. Notice the surface area of the wall we're talking about is in fact A. So I can now say that P would be, I'm going to put the 1/3 out in front again. I'm going to take the N and the M and the V squared average. And now I'm going to write A on the bottom because that's where the area comes from, and the L's on the bottom as well. But looking at that, can anybody tell me what A times L is with respect to our diagram?
Volume.
Exactly. So there's our volume right there. So we can now say pressure times volume is equal to 1/3 N times m times v squared on average. Now that looks pretty good, and we're basically really there, but this is the pressure on an ideal gas times the volume. Now, I can get this a little closer to something more meaningful by multiplying through by 1/2 and multiplying through by 2 at the same time. So if I take this and say, okay, I'm going to multiply by 2 and by 1/2, that's the same thing as multiplying by 1. And when I do that, I get 2/3. And then in addition to the 2/3, I have the capital N, which is the number of molecules. And then I have the 1/2 mv squared bar. Now you might see why I did it. Does anybody recognize what's in parentheses?
Energy.
Yes. This quantity right here is the average kinetic energy. Okay. So if we look at that, we can say, hey, wait a second. I know, for instance, that PV is equal to N times K times T. And I know that P times V is equal to 2/3 N times kinetic energy on average. So combining these two, I get basically 2/3. Notice the ends cancel out. If I just equate the right-hand sides of these two equations and I set them equal to each other, basically what I'm going to get is 2/3 of the average kinetic energy, which would be 1/2 mv squared bar, is equal to K times T. And that's really what we wanted. We're now going to state it, and I'm going to state it in a nice blue equation. I'm now going to state that the average kinetic energy is equal to 1/2 mv squared bar, which is equal to I think, yeah, that's still 2/3. Okay, gotcha. So now I can say to get KT over there, this is going to have to be 3/2 KT. And that's the result I was going for. So you can look at it at this point when I equated it to the ideal gas law. You could look at it as a derivation of the ideal gas law. But what we really did was we postulated the ideal gas law as if it's known, and then we used that to let us figure out what the average kinetic energy of a molecule is within an ideal gas. So that's the actual equation we're trying to use. Any questions on that? All right, so let's do an example. What is, now I want to point out, notice I only took into account when I was doing this, I only took into account the VX's, the VY's, and the VZ's of the actual molecule. And I treated the molecule like it was a really infinitely hard sphere. In doing so, the idea of the sphere rotating or vibrating or any of that kind of weird stuff wasn't really considered at all. So really what I'm looking at is the average translational kinetic energy. So let me write that down. I'm going to put it in red. Average translational kinetic energy. So this is the energy associated with the kinetic energy of the molecules moving in, out, left, right, up, down, but nothing about the molecule, for instance, being shaped like a dumbbell, and therefore each end of the dumbbell has a kinetic energy, or the molecule being shaped like a dumbbell and spinning about its center of mass, let's say like this, are like this as well. So that would be two other modes of rotation. I'm ignoring all those and just saying the translational kinetic energy is what we got here. So this question is asking, what is the average? Whoa, might want to put it back in blue there. What is the average translational kinetic energy of molecules in an ideal gas at 10.0 degrees Celsius and, oh, actually, this is right it. And at 20.0 degrees Celsius. So that's a pretty interesting problem. I wonder how fast the molecules are moving when we're at 10 degrees Celsius, which we learned was 50 degrees Fahrenheit. And then again at 70, which we learned was 68 degrees Fahrenheit. So that might help us. So let's first off say A, 10.0 degrees Celsius implies T in Kelvin is going to be 283 Kelvin. And then B, 20.0 degrees Celsius implies T sub K is equal to 293 Kelvin. Okay. What we know is the average random kinetic energy is 3/2 K times T. So I'm going to say 3/2 times 1.3807 times 10 to the negative 23rd joules per Kelvin times 283 Kelvin. And when I do that math, I get 1.5. Remember, 3/2 is the same thing as 1.5 times 1.3807 e to the negative 23rd times 283. And this gives me, yes, this gives me 5.861. Now I use 3 sig figs on everything, so that 1 is not really a sig fig, but that's times 10 to the negative 21, and that answer comes out in joules, which isn't all that helpful, to be honest with you. Okay, so K on average at 10.0 degrees Celsius is equal to 5.861 times 10 to the negative 21 joules. But we can convert that, for instance, to electron volts, which is a little easier amount of energy. What I know is 1 electron volt is equal to 1.602 times 10 to the negative 31. Well, wait a second. 1.602 times 10 to the negative 19th. I just drew a blank on the charge of an electron. That is bad. Yeah, 10 to the negative 19th. Whew. 1.602 times 10 to the negative 19th. Whoa. And that's the number of joules that's equal to 1 electron volt. So I can convert it that way by dividing by 1.602 e to the negative 19, and that gives me 0.03659. And that's another unit of energy called the electron volt. In this case, the 9 is not significant. So there's the answer for 10 degrees Celsius. So it's really on the order of milli electron volts, about 37 electron volts. Milli electron volts. Okay, notice I use the lowercase m, so it's milli, not mega. Now we can do the other one. The other one, K at 20.0 degrees Celsius, is equal to 3/2 kT. And this is again going to be 3/2 times 1.3807 times 10 to the negative 23rd joules per Kelvin times 293 Kelvin. And in this case, I'm going to say 1.5 times 1.3807 e to the negative 23 times 293, and that gives me 6.068 times 10 to the negative 21st joules. And of course, K at 20.0 degrees Celsius is equal to 6.068 times 10 to the negative 21 joules, which also equals, again, converting it same way, that gives me 0.0378 electron volts. Okay. So you don't necessarily know where that electron volt came from, so don't worry too much about it. That just happens to be a unit we're going to learn a little later, but it's a unit that's a little more helpful when you're dealing with microscopic quantities like, atoms or molecules and stuff like that. Ooh, I don't want to do that. I'm going to say just electron volts, which is on the order of 38 MeV. So, any questions on that one? Your book points out it actually does a problem like this, but in this case, it actually wanted to do one that's at 37 degrees Celsius instead of 10 or 20, which is what I chose. That turns out to be 37, turns out to be 310 Kelvin, and that gives you 6.42 times 10 to the negative 21 joules. So you can see it's a little bit bigger, but not a huge amount bigger. It's 6.4 as opposed to 6.1. But either way, if you actually consider what that means, that's about the kinetic energy that a 1 kilogram stone traveling at 90 meters per second would have. So that's a neat way to think about it, is a mole of molecules would have a total translational kinetic energy equal to, what you do is you take the number that we calculated here, which is 6.06 times 10 to the, or 6.07 times 10 to the 21. We actually multiply that by Avogadro's number, because this is the energy per molecule. So if you multiply that by Avogadro's number, you'd get 3,000, on the order of 3,000 joules. And that is basically comparable to a 1 kilogram stone moving at 90 meters per second. So if a mole of atoms were actually moving at this speed and they all hit you at once, it would not be a easy thing to deal with. Anybody have any questions on that one? Okay. So one thing you want to know is, by taking the square or the average of a square, we get something called the root mean square. So I need to make some sense of that for you guys. So let's do that now. VRMS is actually equal to the square root of the average of the square. Okay. Now, in this case, you could see, for instance, that the kinetic energy is equal to, so for instance, let's say K bar is equal to 1/2, or excuse me, is equal to 1/2 mv squared bar, and that's equal to 3/2 K times T, like that, right? So if you set these two equal, you can see that the 2 down here cancels out with the 2 down here, and you could say that the square root of the average of the square of the velocity is going to be actually equal to square root of 3 times K times T over M. And that is exactly what we called VRMS. So that's another useful quantity. And in fact, it wouldn't hurt to let you see sort of the difference between the root mean square and the actual mean. So let's take 5 numbers. So example. Assume x is equal to 1, 2, 3, 4, 5, and calculate x bar and the square root of x squared bar. Okay. Let's say solution. So x bar would mean x bar is equal to 1 plus 2 plus 3 plus 4 plus 5 over 5. And you see 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. So this would be 15 over 5, which equals 3.0. Now, if we wanted the square root of x squared on average, barred, then what we're going to do is take the square root, but we're going to say 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. All that's going to be divided by 5, and that's going to be 1 plus 2 squared is 4, so 1 plus 4 is 5, plus 3 squared is 9, 9 plus 5 is 14, plus 4 squared is 16, 16 plus 14 is equal to 30, plus 5 squared is 25, so 30 plus 25 is 55 divided by 5, which is just 11. So the square root of 11 is equal to 3.317, roughly. So hopefully that shows you that the root mean square is like an average, but not exactly. So it's fairly close. Notice we got 3 for the mean, but we got 3.31 for the root mean square. So you do in general expect it to be a little higher than the average. A lot of cases, though, the average is just 0. So that's part of the reason why we have to do it. Anybody have any questions on that? All right. So now let's up the ante a little bit. Let's work another example. I'm going to say what is VRMS for helium at 20.0 degrees Celsius and for O2. Remember, oxygen, unlike helium, oxygen generally comes to us in molecular form. So it's oxygen bonded with oxygen making O2, and that's relevant. So we want to calculate the root mean square velocity for this also at 20 degrees. So what we have to do is we have to remember that the average kinetic energy is equal to 1/2 m. And then basically you could say v squared bar like that. So it's the square of the root mean square basically, but that's also equal to 3/2 kT. So for part A, we're going to say helium gas. And for helium gas, what we know is the helium gas has a mass of 2. It's if you actually looked in a periodic table, it wouldn't be exactly 2, but it'd be darn close. So I'm going to look up that real quick just to tell you what it is. Actually, I said 2, I meant 4. It's 4.002. So the molecular mass of helium is approximately 4.002. And you could treat that as atomic mass units, which would be U, and that's the mass per atom. Okay. So if I want to know what the root mean square is, I say 1/2 m v squared bar is equal to 3/2 kT. And then I'd say, okay, well, this 2 in the 1/2 is canceling with this 2 down here. And then I could say root mean square is actually equal to exactly what we found before, which was 3 kT over m. Like that. So now I'm going to say v root mean square, which equals the square root of v squared, the average of v squared, and that's equal to the square root of 3 times k, which is 1.38. Now I said it was 3807, but there's really not much use of me using, all 5 sig figs, so I'll just call it 1.38 times 10 to the negative 23rd joules per Kelvin, and then times T, and at 20 degrees Celsius, that's 293 Kelvin. And then all of this has to be divided by the actual mass of the atom. And the mass of the atom is, in fact, 4.0. That's close enough to give me 2 sig figs. I could even put 4.00 so I can get 3. And then I have to convert that to kilograms. And what I know is that 1U is equal to 1.6605 times 10 to the negative 27 kilograms. So that's what I'm going to calculate. So I'm doing 3 times 1.38 e to the negative 23 times 293. Now I'm hitting divide by, and I'm using the left parenthesis. I'm going to say 4 times 1.6605. That one I could have just rounded off at 1.66 as well. That's not a big deal. But e to the negative 27. And then I say close parentheses. And what I have now is the stuff that's under the square root. So I'm going to say this is the square root of 1.826. That's 1 extra sig fig times 10 to the 6th. And all of these units tell me, notice the kilogram or the Kelvin cancels out with the Kelvin right here. The joule is a 1 Newton meter, which is actually equal to 1 kilogram meter squared per second squared. So if I divide a joule by a kilogram, I get meters squared per second squared, and that's it. So I can put in here meters squared per second squared. That's my actual unit, and I get VRMS, which is defined to be V bar of V squared, is actually equal to, I'm going to take the square root of this answer, and this is going to give me 1,351 meters per second. And that's one extra sig fig than I have, so I really should call it 1.35 times 10 to the 3 meters per second. So you can see that's really, really, really fast. We're talking on the order of 1,000 miles per hour. And this, of course, was helium at 20.0 degrees Celsius. Now I can do part B, which is for oxygen. And in that case, it's O2, and that means the mass of O2 is, looking at the periodic table, you'll see that the O2 has a mass of 15.999. So I'm going to essentially call it 16.0 U. So now I can say VRMS, which is equal to the average of the square of the velocity, take the square root, and that gives me the square root of 3 times 1.38 times 10 to the negative 23rd joules per Kelvin times 293 Kelvin. All that will be divided by 16.0 U times 1.6605 times 10 to the negative 27 kilograms per 1 U. And this should give me the answer. So 3 times 1.38 e to the negative 23 times 293 divided by, now I'm going to do parentheses, 16 times 1.6605 e to the negative 27. Close parentheses, that gives me that. Now I'm going to take the square root of all that. This gives me 675.7 meters per second. Oh, crap. That's wrong. I did tell you that the mass of oxygen was 15.9, but here's my mistake. This is the mass of oxygen, and this means the mass of O2 equals about 32.0. So let me correct that, and I can then say divided by square root of 2. That gives me 477. That's better. Okay. So I'm going to erase this, and what I'm going to erase is this 16U here, but I'm going to write inside of there 32.0U. Now this gives me 477.8 meters per second. So I'm going to say VRMS, which is equal to the square root of the average of the square of the velocity and that's equal to 4.78 times 10 to the 2 meters per second, and that's for O2 at 20.0 degrees Celsius. Any questions on that? So when I was telling you about equilibrium being the atoms or molecules in one object have the exact same kinetic energy of the atoms or molecules on average in the other object, then when you put them in contact with each other, they're automatically going to be in thermal equilibrium because one, the average kinetic energy is a measure of the temperature and they have the same average kinetic energy. But what that also means is that one of the objects colliding has an atom or molecule colliding with one of the atoms or molecules from the other objects is likely to not give it any more energy because it already has the same amount of energy. On average, of course, we know there's a distribution of speeds. So there's going to be some really, really fast ones that occasionally hit a really, really slow one. And that's going to make the really, really slow one speed up. And it's going to make the really, really fast one slow down. But on average, that's happening just as much as the other way around. So that's ultimately what causes the equilibrium is the fact that they have the same kinetic energy total on average for the individual molecules. So anybody have any questions on that? All right. It's 6:57. So what I'm going to do is go ahead and give you guys, let's go ahead and give you till 7:05. And we'll take a break now. Okay, I'm here if anybody has any questions, but we have a break until 7:05. We've got about a minute left, everybody. All right, so let's get started, everyone. Anybody have any questions on anything we've done so far? We don't have a whole lot of time left, but we can certainly finish out the rest of the stuff. It's not very terrible. What I did want to point out to you, I wrote down at the bottom, interesting information. So one of the things you learn if you're an astrophysicist, especially one interested in planets, is that for starters, when a planet first forms in around around the star system, or around the star in general, it normally has dissolved gases in the actual solids that make it up. And when it starts to collect all those solids can build up such high pressures and temperatures, at least below the surface of it, that ultimately those gases are released. And those gases are released, and normally gravity holds on to them. So they lift up above the high density, what you'd call the solid material that makes the planet, and then they just make a little envelope of gas above the actual surface of the planet, and that's what we call the primordial atmosphere, or also the initial atmosphere. Well, if you know the average temperature at the surface of that planet, then you can actually figure out what the average velocity, the root mean square velocity, is for every particular gas that's in that initial atmosphere. If that average, or if that root mean square velocity is as high as 1/6 of the escape velocity for that planet, then given enough time, on the orders of tens of thousands of years or something like that, that gas will disappear. So that tells us a lot of information about how gases, or how planets have specific gases in their atmospheres and not other ones. So that's just something I wanted to point out for you. And that's why some of these calculations are so valuable, because you can actually see that they are giving you actual root mean square velocities of individual atoms, and therefore you can from that go ahead and calculate things like which one of these gases is going to be present after a long period of time. Now, I will tell you also that it's very well, it's not uncommon for the initial atmosphere of a planet that it created itself from off-gassing, that will sometimes completely be blown away, and later an entirely different atmosphere form. That's also what happened with our planet Earth. Specifically, once we got enough water bombarding and getting on the surface, then water started to help some things. And then we had life that actually occurred below the surface of the water. That actually switched the atmosphere up considerably, switching from a largely oxygen-based atmosphere, and oxygen was actually, well, I should say, largely carbon dioxide based to some extent. But either way, the main thing is the actual green plant life and algae and stuff like that could actually change the composition, because photosynthesis takes in CO2 and produces oxygen. So we could take a low oxygen atmosphere and make it a high oxygen atmosphere by having a ton of plants. If we had instead a ton of animals without plants, then we would make it mostly CO2 without oxygen. But that's often what happens in the end game. So anybody have any questions on that? All right, so the next section is on the distribution of molecular speeds. And of course, the 2 photos for this class are actually the 4 photos for this class are Maxwell, Planck, Bohr, and Einstein. And Maxwell, it turns out, is actually a big deal in everything. So we're going to do electricity and magnetism, and basically Maxwell wrote the 4 equations that were named after him by using Faraday's notebook, where Faraday had completed a lot of the understanding just qualitatively and to some extent quantitatively, because just he wasn't a mathematician and wasn't mathematically gifted, so he couldn't actually express them that way, but he expressed them so precisely that Maxwell was able to translate them into equations, and then even found something that was missing that Faraday hadn't discovered yet. So he wrote out the 4 equations of electricity and magnetism, and if you can ignore quantum mechanical effects, that's all you'd ever need for electricity and magnetism. It literally, Maxwell gave us a complete product, not unlike Einstein did with the special theory of relativity and to some extent the general theory of relativity. Maxwell did that. But in addition to that, Maxwell was the first person to ever tell us what the rings of Saturn were made of. There was an idea that the rings might actually be disks, and he proved that that couldn't be it, and he did it with just statistics and mathematics and physics. And for instance, one of the things he did was he imagined the existence of atoms and used basic statistics to figure out what the distributions of speeds of the individual atoms or molecules in a gas would be. And in so doing, he gave us what's now called the Maxwell distribution, or the Maxwell-Boltzmann distribution. This one, your book's just calling it the Maxwell distribution, but this is it. It's the f of v is equal to 4 pi n parentheses times m over 2 pi kt, close parentheses, and all of that's raised to the 3/2 power, times v squared times e to the negative 1/2 mv squared over kt. That, and actually that's not that terrible of a derivation. I've done it a couple times myself. It's really that easy to follow once you know some basic rules about combinatorics. For instance, if you know how to calculate how many wrong answers there are for playing the lottery, then you know combinatorics. So if you can do that, you can do it. It's really mostly about for instance, in our 5 factorial, are y'all familiar with the numbers factorial? You probably might have ran into it in Calc 2 if you've had that. But basically 5 factorial, which is 5 with an exclamation point after it, is understood to be 5 times 4 times 3 times 2 times 1. And once you have that idea down, you can make up all sorts of formulas with that stuff. And in so doing, he got this Maxwell distribution, and there's a graph of it down at the bottom of this list of things that I wrote down. And there's a sentence that explains to you what f of v is. Specifically, if you multiply f of v by a small change in v, the velocity, that small change would be called dv. So f of v times dv should give you the number of molecules that have a speed between v and v plus dv. Now, if you integrate that from 0 to infinity, then you're taking into account all the possible velocities that could occur. And since the original assumption is that an ideal gas has n molecules, and we're actually treating this for an ideal gas, but in principle, it works without even an ideal gas. But because of that, you know that that integral from 0 to infinity should be n. And that's actually where the m over 2 pi kt to the 3/2 power comes from, because it turns out until you do this part of what we call normalization, you're not actually going to get the full correct answer. But with that distribution, what you can see is this plot has a peak, meaning the curve goes up and then reaches a point at which the slope is 0. That's the peak velocity, not meaning it's the velocity, the fastest velocity they will have, but meaning it's the velocity that they have at the peak of the curve. If you go a little further along, though, then you get the average velocity, and that's what I call a v-bar. And if you go a little further along still, you get the root mean square velocity. And now that we have a formula for that root mean square velocity, you might want to know is, hey, does this Maxwell distribution give that? And it does. And in fact, I highly recommend you guys doing these following operations. I'm going to do one of them for you, and then your book does the other ones. I think your book also does the one that I'm going to do, but from that, you can do it on your own. So what I'd like to do, for instance, is calculate the V sub p, which is the velocity at the peak, but it's also called the most probable velocity. So VP equals velocity at peak, but it also equals most probable velocity. So the most probable means we maximize it. Oh, crap. Okay. So if V were, for instance, to give us the f of V was to give us the number of molecules with a velocity between V and V plus dV, when we multiply it by dV, then we should be able to take the derivative of F with respect to V and get us set that equal to 0, and that should give us our most probable one. So let's do that. And this will be example 5, maybe. Example 4. Oop, wait a second. Yeah, example 4. So df of v over dv is equal to 0. Now, what this gives you, notice the only thing that has a v in it is the v squared and the e. So I'm going to say this is 4 pi n all that junk, which is m over 2 pi kt to the 3/2 times d by dv of v squared e to the negative 1/2 mv squared over kt. And I'm going to set that equal to 0. So you can automatically tell that I can divide both sides by 4 pi n to the 3/2 divided by 4 pi n blah 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 to the 3/2, and ultimately that's just going to give me, for instance, if I take this is a product inside the parentheses, so what I'm going to get is I'm going to take the derivative of v squared first, and that's going to be 2v times e to the negative mv squared over kt. And now I'm going to say plus. Now this time I'm going to leave the v squared, but I'm going to take the derivative of e to the negative 1/2 mv squared over kt. So I know, for instance, that I'm going to have to take the derivative of e to the u and then multiply that by du dv. So the derivative of e to the negative u is basically e to the negative 1/2 mv squared over kt times the derivative of the actual exponent. So when I take that, it's the derivative of v squared is going to be 2v, and that 2 is going to cancel out with the 1/2. So I'm going to get minus mv over kt like that. And that all looks good to me. And that's all equal to 0. you can immediately see that this quantity and this quantity can't make it 0. So from this, I'm going to say that 2v minus mv cubed over kt has got to equal 0. You can, of course, divide both sides by v to get rid of one of these. Oops. So that gets rid of that one and that one. And now I have a v squared over here. So basically what we get is v p is equal to the square root of 2kt over m, which is about 1.414 times the square root of kt over m. So that's a worthwhile thing to do. Another thing to do would be, and it would be worthwhile, is to calculate the average velocity. So example 5, use the Maxwell distribution to derive V bar. So I'm going to give you a blueprint of how that goes, and I'll let you finish it on your own as something you should do just to be prepared. And you can look up integrals on the integral tables and all that good stuff. But what I'll tell you is that V bar is basically gotten by taking the integral from 0 to infinity of v times f of v dv, and then dividing it by n. So remember, the probability is the integral of f of v dv. Oops, that's a d in there. Let me fix that real quick. It looks like a d in anyways. So dividing it by n actually gives me the average. If I wanted to know the average of the square, then I'd put in a v squared there. So I could, for instance, say v squared bar. That would be the integral from 0 to infinity of v squared f of v dv, and all that would be divided by n. Okay. If I wanted to know the ones cubed, I'd put a v cubed in there, so on and so forth. But what I'm going to do is this first one. So when I put this in, I'm going to say it's equal to 1 over n times the integral from 0 to infinity of 4 times pi times n, which obviously can come out, times m over 2 pi kt to the 3 halves. Now, I had a v squared in there already. Notice the v squared in the formula for f of v. So I'm now multiplying that by another v, and that's going to give me v cubed, and then e to the negative 1/2 mv squared over kt. Now, what I have to do with that is, of course, multiply it by dv and compute that integral. You can automatically see that the n's cancel out like that, and the m over kt is going to come out in front. So I'm going to go ahead and say, let's go ahead and say 4 times pi times m over 2 pi kt. All of that would be to the 3 halves power. And then we're going to have the integral of from 0 to infinity of v cubed e to the negative 1/2 mv squared over kt times dv. And they tell you in your book to use integration by parts. And that's specifically why I want you to do this on your own, because this is something that we do teach in our calculus class, but I've seen a lot of evidence to suggest that people don't necessarily get it. What integration by parts is the integral of u dv equals uv minus the integral of v du. That's the integral by parts. What you want to do is notice in going from the left-hand side to the right-hand side, you have to, in some sense, integrate. Dang it, I was supposed to use a different color. You're supposed to integrate this because you can integrate dv to get v and then put the answer right there. And then you take the part right here, which is easy to differentiate. You differentiate that. And you put it right there like that. Okay. So in principle, when you go to try to use integration by parts, you want to take one part that is virtually impossible to integrate, and you're going to do the derivative on that. But the other part should be easy to integrate, and of course has to include the dv. And then you can convert it to this other right-hand side. So for instance, what you might do here is you might say, well, I've got a v cubed and an e to the negative v squared over kt. Both of those are super easy to differentiate. V cubed is easy to integrate. V cubed dv is easy to integrate. E to the negative mv squared over kt is not necessarily that easy to integrate, but we have tables on it. So you can play with that, or you can just look it up on an integration table. But I will tell you that ... the answer turns out to be the square root of 8kt, that's 8 over pi specifically, divided by m, like that, which is approximately equal to 1.60 times the square root of kt over m. Okay, so that's the way you can get it, and I'll just say and it turns out if you wanted to do the squared, of course, this one ends up equaling the square root of 3kt over m, which is exactly what we already had. And of course, that's approximately 1.73 times the square root of kt over m. Okay. All of those things are worthwhile. I really don't need you to do any more than the one that I did for you, which was finding the most probable, and then the one that I sort of gave you an outline for doing. So just try to get those done on your own. Feel free to send me text messages or emails for any help you might have, might want, or whatever. But we're now finished with section 18.2. Any questions on that? All right, so the rest of chapter 8 is really about real gases and change of phase and that sort of stuff. And it does a lot of PV diagrams and all that good stuff. So it's mostly about reading. So when we talk about section 18.3, it says real gases and changes of phase. The ideal gas law, PV equals NKT, is an accurate description of the behavior of real gases as long as the pressure is not too high and as long as the temperature is far from the point at which it becomes liquid. So you should start to see things starting to deviate a little bit from the typical ideal gas law as you get closer and closer to liquefaction. So what they mean by that is this. This is subsection 18-3. So if you made a pressure versus volume diagram, volume here, pressure here, for an ideal gas. If you did that, what you'd have is P equals nRT over V. So for a given temperature, you would have a curve like this. And another temperature, you'd have a curve like that and a curve like that. So all of those are different temperatures. And this one would be a higher T. Actually, let me do this. Okay. Now, as you start to get far, what we'll discover is there's this little region where liquefaction occurs. And in fact, we got a liquid vapor occurring. As that starts to happen, then the curves start to look like less of the ideal gas law, and you'll see like that are that and stuff like that. So that's where the ideal gas law fails. Because of liquefaction. So that's the first thing they want you to see. I want you to also know, of course, they've got bold print in here. So they say liquefaction as one bold print thing. And that means liquefaction as a substance becomes a liquid, also called condensation. So when you're going from the gaseous stage to the liquid stage, phase, I should say, that is actual condensation. So, for instance, if you leave a cold, let's say, Pepsi bottle outside on a hot day, what will inevitably happen is the cold air around that cold water-based Pepsi is going to make the temperature right around that bottle a little lower. And if that temperature really is low enough, then it'll actually pull water out of saturation into the actual gas. In other words, it'll cause it to condense out, not unlike clouds having water condense out to make the clouds. This is the same thing happens here. So you'll get little water droplets that come from the atmosphere, and they'll appear on the outside edges of the Pepsi bottle, or even just a ice cold glass with water in it, or ice cold glass with tea or beer or anything like that on it. That's going to get condensation built up on the side, and that's strictly because you've changed the condition of the atmosphere immediately around the cup or the bottle or whatever. There's also going to be something called the critical temperature, and that's the point where the curve C goes horizontal, and the actual temperature is the temperature at which it occurs. So that's the critical temperature, and then the critical point is the point on the graph where it happens. So there's some different sort of terminology and stuff that you'll see in bold print. You should be aware of those. There's even critical temperatures and pressures listed in a table. For instance, the critical temperature for water is 374 degrees Celsius, or 647 Kelvin, and the critical pressure is 218. For CO2, it's 31 degrees Celsius, 304 Kelvin, and the atmospheric pressure has got to be, or the critical pressure has got to be 72.8 atmospheres, so on and so forth. There's all sorts of diagrams like that. There's a diagram for CO2, as well as a diagram for water. And one of the things you'll notice, for instance, for water, if you do pressure versus temperature, for H2O, what you'll find is that there is this little line that comes up like this, and then it breaks off and goes this way, but it also breaks off and goes this way. And what we have over here is solid. What we have over here is vapor. And what we have over here is liquid. And this point right here is called the triple point. Okay. If you look at CO2, you'll see it's a little bit different, and that's why I'm taking the time to draw this really quick. Here's temperature, here's pressure, and this is CO2. And in this case, what you get is a quantity that goes up like that and then breaks off like this. And again, we get solid, vapor, and in this case, you get liquid. And again, you have a triple point. But you can see how those curves are different, and that's something that's a big deal with regards to water versus carbon dioxide. So that's something worthwhile reading. I'm trying to remember if there's anything specific. It does talk about helium-2 and superfluidity and liquid crystals. Most of that stuff will be helpful to you when you're doing the concept questions. There's not a lot of these things aren't that critical when you're going to try to solve physics problems, but some of them are. So make sure you do read it as closely as you can. The next step is vapor pressure and humidity and evaporation. And basically just know from the atomic theory that evaporation happens basically when you have the liquid in a liquid state, but the surface tension is insufficient to keep the molecules from escaping to the gaseous state for various reasons. And those various reasons could be things like the temperature's high, the pressure's low, all sorts of good stuff like that. So that's listed in there. Again, just more reading. The vapor pressure, though, your book actually has a saturated vapor pressure of water table. And that's kind of important because what I told you when we did the ideal gas law, if you ever collect a gas over a liquid, and then you're asked something about the pressure of that gas above the liquid, a new gas might have actually been formed above the liquid, but there's going to be water vapor above it because you're doing it above the water. And what you have to do is say, okay, well, there's going to be some pressure due to the new gas that was created. Let's say it's oxygen, and we can find that pressure, but the actual pressure total inside of there is going to be that pressure plus the vapor pressure of the water, which you can look up on a table. And you see, for instance, at -10 degrees Celsius, the vapor pressure of water is 2.6 times 10 to the -3 atmospheres, or 2.6 times 10 to the second pascals. So that is just something that'll help you. It does give you units like bars, millibars, pascals, and millimeters of mercury as various pressure units. But that's basically it that's relevant from 18.4. Except after that, 18.4 talks about boiling. And what I want you to understand with boiling is, again, you have surface tension. And the reason why surface tension even exists is, let me draw this diagram so you'll make some sense of it, or be able to make some sense of it. So let's imagine this is the surface of water. Now, what we know from the atomic theory of matter is this surface is really an atom, 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 and so on like that. And then there's more rows of atoms down here. They don't necessarily have to be perfectly set up like this, but it's a little easier to see if you imagine them being perfectly set up like this. But what I want you to understand is, let's look at, say, one of the atoms in the middle row specifically. So let's imagine, for instance, this atom. This atom has this atom pulling on it. It has this atom pulling on it, this atom pulling on it, and this atom pulling on it. And that would suggest to you that the net force on that atom is nothing. So it would take very little for you to move that atom out of the way. But if you now examine this atom instead, or this molecule instead, what you'd see is this molecule is pulling on it, 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 and this molecule is pulling on it. So if I go to try to pick up that particular molecule, the molecule to the left and the molecule to the right cancel each other out laterally to some extent, but nothing cancels out vertically. So I can't just pick up a bit of water from the surface. That water is going to come up with that little atom that I try to pick up. And that's what we call surface tension. So how does this relate to boiling, for instance? So a liquid will boil when its saturated vapor pressure equals the external pressure. In other words, what's going to happen is slowly the individual atoms are going to break through that surface tension and become a little wafer, if you will, of water vapor above the water. Okay. Once that vapor pressure is saturated, meaning you've got the maximum amount of water dissolved into the air, once that pressure that it has when the maximum amount of water is absorbed by the air, once that pressure is the same as the atmospheric external pressure, then more atoms can come up and boiling begins. Okay. So that's the idea of what boiling is, and that's something that's helpful. I will remind you that partial pressures and humidities are relative things. So hopefully you recall this from intro to chemistry or beginning chemistry in high school. But for instance, let's say our atmosphere is 80% nitrogen and 20% oxygen, and there's nothing else. If that was really true, it would be a lot easier to calculate. We know it's not quite true, but it's close enough. So if the pressure is in fact 1 atmosphere, then the partial pressure of oxygen would be 0.2 atmospheres, because if you multiply 20% times 1, you get 0.2. Similarly, the partial pressure of nitrogen would be 0.80 atmosphere. That's because the percentage of nitrogen is 80%, and if you multiply 80% times 1, you get 0.8. So that's what partial pressures are. You got to keep that in mind. So if you want to know what fraction of the total pressure a gas is, what fraction of that is due to nitrogen, you just multiply the percentage of the gas that's nitrogen by the total pressure, and that'll give you the partial pressure. Now, the thing that goes on this is something called relative humidity. And I'm not going to require you to do this for tests, but I am, it's something that everybody should sort of know. So I definitely like you doing it on practice. So the relative to humidity is the partial pressure of water divided by the saturated vapor pressure. And then, of course, you make it a percent by multiplying by 100 and tagging a percent on the end. Okay. So your book does a nice example. On a particular hot day, the temperature is 30 degrees Celsius and the partial pressure of water in the air is 0.030 atmospheres. What's the relative humidity? So that's a typical example. This will be example 6. And it says T equals 30 degrees Celsius. PP of H2O is equal to 0.030 atmospheres. And they want to know the relative humidity. Okay. So the solution here is not terrible. I'm going to go back and look at the table, and I need to find out the saturated vapor pressure of water. So if I go back and look at the table, which I think I found further back here, there it is. Saturated vapor pressure, water, 30 degrees Celsius. So table from your book, it's called table 18-2. If you look on that table, you'll find at 30 degrees Celsius, the vapor pressure, and they said atmospheres, saturated vapor pressure is equal to 0.042 atmospheres, or it's also equal to 4.24 times 10 to the third pascals, but this is the value we're going to use. So now I can say relative humidity is equal to the partial pressure of water, which is 0.030 atmospheres divided by 0.042 atmospheres, 0.42, yeah, that's right, atmospheres times 100%, 0.03 divided by 0.042. That gives me 71.4%. So that's the relative humidity. Obviously, that 4 is not a sig fig, but that's just a simple case of how to do relative humidity. I just want to show you one little example. It also has a nice conceptual example in 18.7 that it works for. Temperature decrease of boiling water with altitude. The book does a really good description of that. I would say subsection 18-5. Ooh, 18-5, not 15. Okay for homework, but not test. This is the same as true. Okay for homework, but not test. Okay. After that, I think that's the next to the last section, van der Waals equation. I'll tell you one of the ways they tried to make the ideal gas law a little better is they used the Clausius statement. Excuse me, the Clausius statement, the Clausius equation of state. And basically what we realize is that the atoms or the molecules making up the gas are actually have a finite size. So some of that volume that you normally have is actually spoken for by actually having atoms and molecules. So instead of PV equals nRT, they do P times V over N minus B is equal to RT. And N is the number of moles as normal, but this B value comes from a table. So that's the first iteration. The second iteration is van der Waals equation, and that's VAN DER and then capital WAALS equation. And in that case, van der Waals equation tries to take into account not only the diameter of the molecules mattering, but also how they sort of attract one another. So you end up getting P plus A over V divided by N quantity squared times V over N minus B, and all that's equal to RT. So these basically come from a table and come from a table like that. So these quantities come from a table. So anything more than just looking up the value on the table and then solving for P or V or T or something, anything more complicated than that, you're definitely not going to have on the test. But you'll definitely have all sorts of stuff on the homework and easy stuff like that, possibly on the test. The mean free path, I'm not going to cover at all. So that's 18.7. And 18.8. I'm not going to cover that as well. So both of those sections aren't going to be on the test. I don't think I left anything in the homeworks on them either. So you shouldn't have that. And I tried to cut out the diffusion problems and the mean free path problems from the tests and practice tests. But that's it. We're done with chapter 18, believe it or not. You guys are free to go. Time's up. Make sure you keep an eye out for the online tests and start doing that. Remember, you get plenty of trials. I think I normally give you at least 3, and I only take your highest. And yeah, thanks, Sebastian, for catching me on my 32U instead of 16U. I wish I would have saw that earlier now. But you guys are free to go. I'm going to wait for the last person to leave in case anybody has any questions. And you're free to go. Thanks again for coming. And have a nice evening. And keep me posted if you need anything. It looks like everybody is gone.